Welcome to Lecture 6, Section 2. This video will cover taking inverse Laplace transform using partial fraction expansion with functions of real roots. Taking the inverse is the third step in the Laplace transform process we are using to solve ODEs. The first step is to transform the first order differential equation ft by taking the Laplace transform. Step 2 is to solve for fs in the Laplace domain. This is usually done with algebra. Step 3, the final step, is to transform the Laplace expression fs into the equivalent expression ft in the time domain using partial fraction expansion. We introduced the idea of using partial fraction expansion in Lecture 6, Section 1 video. To write a partial fraction expansion of a Laplace function, we need to find roots of the denominator and coefficients needed in the numerator. Once we have the partial fraction expansion, we will take the inverses by finding the expressions in column 3 of the Laplace transform table in the course packet. Remember that the goal of the partial fraction expansion technique is to find a series of simple expressions that are equivalent to the original Laplace expression fs, which can also be written as a ratio of two polynomials bs over as. These two polynomial expressions are functions that include constants s and powers of s, including s squared, s cubed. When we find roots for the partial fraction expansion, we can have four cases. The first case is when the roots are distinct and real. This is the case we will discuss for this video. The second case is then the roots are complex numbers and include the square root of -1. This will be covered in the next video. The third case is when we get repeated roots and covered in another video. Finally, the last case is when the expression fs is already in form that we can find in the third column of the Laplace transform table. Then we don't need to use the partial fraction expansion technique. So for case 1, we get distinct real roots. That means that all of the roots are real numbers. They can be positive, negative, or decimal values. They don't include any square root of -1 values. So when we have only real roots, we will write fs as the sum of several Laplace terms that add up to the original expression fs. The common convention is to use a's for the numerator coefficients and p's in the denominator. So we need to find all the a's and p's. In Lecture 6, Section 1 video, we covered one way to find the roots. For simple equations with degree 2 terms, we can use the quadratic equation. To write the partial fraction expansion expression, we need to find the a's in the numerators and the roots in the denominator. The most convenient method to use is to use MATLAB and the residue function. You can put in the polynomial coefficients and MATLAB returns the numerator coefficients and the roots. In many examples in the course packet, the root function is used too to clarify which values are the roots. Before using MATLAB, we will demonstrate how the numerator coefficients, the a's, can be found by hand. The manual method is described on page 65 of the course packet. We will not use this method very much because we can find a's and p's using MATLAB. But I want you to be aware of the technique in case you need it. To use this method, we need the roots. Then, to find each a term, we multiply both sides by s plus p, set s equals to minus p, solve for a, and repeat the process for each term. The easier method is to use MATLAB to find both a's and minus p's using the residue function. To use residue, it is more convenient to write the Laplace function as the ratio of two polynomials. Here we have bs written as a polynomial using q as the constant coefficients in the numerator, and as is written as a polynomial using g as the constant coefficients in the denominator. You will learn more about residue in lab in the future week. The residue command is written as square bracket a, r, k equals residue with the numerator coefficients. Here is the example shown in the course packet on page 66. We start with the ODE dx over dt plus x equals 1. The given initial condition is x0 equals 0. The first step is to take the Laplace transform of the ODE. Taking term by term, the Laplace of the first term, dx dt, is x times s times xs minus x0, where x0 is the initial condition. The Laplace of the second term, x, is xs. The Laplace of the third term, 1, is 1 over s. Combining terms produces s times xs minus 0 plus xs equals 1 over s. The next step is to use algebra to solve for xs, which turned out to be 1 over s times s plus 1. You can find the roots using the MATLAB root function, or after some time, you might see that the denominator roots are 0 and minus 1. We could invert this expression directly. This is the Laplace domain expression for equation 19. But I want you to solve it using partial fraction expansion. We can write the partial fraction expansion of the expression as a1 over s plus a2 over s plus 1. The next step is to find a1 and a2. To find a1 by hand, we use the equation from page 65. We multiply both sides by s plus 0, and then we set s equal to 0. We end up with an expression with s in the numerator and the denominator. S over s cancel each other. Then we set s equal to 0. The result is a1 equals 1 over 1, which equals 1. Similarly, we can find a2 by multiplying both sides by s plus 1. We get a2 equals 1 over s, with s set to be minus 1. Then we get a2 equals minus 1. Now we insert the terms to write xs equals 1 over s minus 1 over s plus 1. We can find these expressions in column 3 of the Laplace transform table. They are equations 5 and 15. Taking the inverse, we get xt equals 1 minus e to the power minus t over 1 minus e to the power negative t. For simple expressions, it is not too hard to do by hand. If we redo example 1 using MATLAB, it is more convenient to write the numerator and denominator as polynomials. In this case, it is 1 over s squared plus s plus 0. 0 is intentionally added to make sure that we don't forget that last term of the polynomial expression in the denominator. In MATLAB, we will type in ark equals residue 1, bracket 1, 1, 0. Make sure you write the expression correctly using the format shown here. The first square bracket contains the numerator coefficients separated by spaces. The second square bracket contains the denominator coefficients separated by spaces. MATLAB will return A1 equals minus 1, A2 equals 1, R1 equals minus 1, and R2 equals 0. Given the residue command results, we can write the partial fraction expansion using the a's and r's as negative 1 over s plus 1 plus 1 over s plus 0. It is important to keep the subscribed terms together. After reorganization and simplification, we get 1 over s minus 1 over s plus 1. Taking the inverse using the Laplace transform table produces xt equals 1 minus e to the power minus t. Here we have example 2 from the course packet on page 6-7. Fs equals the ratio s plus 1 over s squared plus 3s plus 2. The residue command is shown here. ARK equals residue bracket 1, 3 and bracket 1, 3, 2. MATLAB will return A1, A2, R1, and R2, and we can plug these results into the partial fraction expansion using the roots, which produces this expression. Fs equals minus 1 over s plus 2 plus 2 over s plus 1. These expressions can be found in column 3 of the Laplace transform table. In this case, we use equation 15 twice. The time domain result is ft equals e to the power minus 2t plus 2 times e to the power of minus t. Now you have all that you need to start the next problem set. You can use MATLAB to do the homework following this instruction. This is the end of the video for Lecture 2, Section 2. Lecture 6, Section 2. Write down any question you may have from this presentation and please bring them to class. Thank you.